this computer. Wow, that was loud. Okay, so let's do a little recap. Good afternoon, everyone. Dr. Nat here. So yesterday we were talking about interrupt. We had two types, which was the nested interrupt and the sequential. What was it? Okay, so this is the first one. We talked about sequential interrupt processing, whereby if the user program gets an interrupt call, it processes that interrupt and disables any other interrupts that is called out by other I/O devices. So this is sequential, meaning to say it has to finish the first one that calls upon the user program before dealing with the next one. So that is why it's called sequential interrupt processing. And then we had the nested one, which we had to define the priorities. And yesterday, one of you asked a really good question. Is it possible to have the same priority for the different I/O device? So when we are talking about priorities, you can say that, oh, my girlfriend and my mom is the same priority in my life. But in reality, we know that even though we say that they have the same priority, there's always going to be one having the advantage over the other, not advantage, a priority higher than the other, even though it's a little bit only. So that is why we have to define the priorities. And in your exam, if I were to ask this question, I would tell you which one has the higher priority. There's not going to be a similar priority device. Okay, so that was a good question. So those are the two approaches for multiple interrupts. So this is how the user program handles multiple interrupts. Before we talked about the multiple interrupts, we also talked about how the user program handled interrupts, single interrupts, right? So hopefully everyone has an idea of how that works. And then we also talked about this example whereby we had the disk having lower priority than the communication line, but the communication line has a higher priority than the printer because the printer is slow. So, and the priority is dependent on how critical the data is. Are you going to lose the data over a small period of time? So those are the things that define the priority. Okay, and then we talked about the I/O function. Previously, we were talking about how the CPU exchanges data, reads and writes between the memory. And also we know that the CPU or the processor also does this with the I/O devices. And this is the I/O function or I/O modules. So this was what we talked about yesterday. And this is the top level view. That is the basis to our chapter, this chapter at least. And then we talked about the different modules, the memory modules, the I/O modules, and the CPU modules. The memory and the I/O have the read and write operation, and they have inputs and outputs, whereas the CPU, the difference is that it has the control signal. Of course, the CPU is the brain. Okay, and then we also talked about how are these different modules connected to each other? What are the paths like? So the path between these modules is called the interconnection structure. And we also talked about the different types of interconnection structure. Oh, sorry, excuse me. We only discussed one type, which was the bus. Where is it? Oh, this one. The bus and various multiple bus structures, and the second one, point-to-point interconnection structures with packetized data transfer. We only talked about the bus. So let's go over to the bus. Did we talk about this one yet? I don't remember. Oh, yes, we did. So I told you your bus width increases over time. And sorry, you've seen over the years that your bus width increases over time, and you've seen this in your assignment as well. So the bus width is so several lines of a bus can be used to transmit binary digits simultaneously in parallel. For example, an 8-bit unit data can be transmitted over 8 bus lines. So the more bus lines that you have, the more data that you can transmit. We talked about this yesterday. And we also talked about the data bus. And we also talked about the address bus and the control bus. I told you the address bus is used to designate the source or destination. It's like a postal service, whereas the control bus is the authority that handles all the mailing data. So not everyone can see the mailing data, right? So this is the control bus. And then I told you, if one module wishes to send data to another module, it can be CPU to memory and memory to IO, depends. First, it has to obtain the permission from the bus, and then it transfers to the bus. So this is very important because we are going to talk about how permission is granted in a bit. Okay. And I skipped this part, so I'm going to go over this one today. So we have 2 bus configurations. One is the traditional, or I flipped it. One is the traditional and the other is the high performance architecture. So let me use my pen. Oh, what happened? Okay. Okay, so we have 2 bus configurations. The first one is the traditional, that is so big, traditional bus architecture. Okay, so here we see that there is a local bus. There is a local bus over here. Sorry, this one is the local bus that connects the processor to a cache memory. So you see that there is a local bus connecting the processor to the cache memory and may support one or more local devices. Okay, let's see what that means. The cache memory controller connects the cache not only to this local bus. This cache is not only connected to this local bus, but to a system bus over here. So it has 2 buses connected to the cache. One is the local and one is the system bus. The local is dedicated to the processor, and the system bus, which are attached all of the main memory modules. So here you see that the system bus is attached to the main memory. But this is different than what we have seen earlier on. We saw that the system bus was something like this, if I'm not mistaken. We had the CPU, the memory, and also the IO, and we called this the system bus. This was the top level view. But as we go deeper, we can see that there are different ways to arranging this, and this is one of it. This is the traditional style, and you have a system bus connected to the main memory, and the system bus is connected to the processor, but the cache acts like an insulator. It acts like an insulator. And then the system bus is also connected to the IO, but via the expansion bus interface. The expansion bus interface acts like a controller or a buffer between the IO devices, where we have the expansion bus that is connected to the network, SCSI, what is that? The small computer system interface. And then we have the modem, the serial. These are all IO devices. Okay. What else do we need to talk about here? The use of the cache structure insulates the processor from a requirement to access main memory frequently. So whenever it has to access memory, it doesn't necessarily have to go through the system bus. It can access through the cache. The cache handles this arrangement. Why? Because in this way, the IO transfers, hence the main memory can be moved off the local bus onto the system bus. In this way, the IO transfers to and from the main memory across the system bus do not interfere with the processor's activity. So whatever that is happening here, it is insulated by the cache, meaning to say that remember that we talked about the IO can exchange data with the main memory, it can read and write to the main memory. So it can happen independently of the processor if the processor has granted the authority to the IO. So the cache insulates and allows that independency to happen. An expansion bus interfere buffers data transfers between the system bus and the I/O controllers. So here we have the expansion bus interface also acting like an insulator or a buffer between the system bus and the I/O controllers over here. The arrangement allows the system to support a wide variety of I/O devices. So here you can see that there are a lot of I/O devices. And at the same time, insulate memory to processor traffic from the I/O traffic. So if we have traffic over here, it is insulated. These guys over here are insulated from the traffic over here. Same case, if there is a traffic over here, the processor is insulated by the cache from the traffic going on over here. So this allows us to have a more efficient coordination. So, but however, this configuration begins to break down, as in the performance deteriorates as higher and higher performance is seen in the I/O devices, as it is quite obvious because our graphics card is constantly upgrading. So as the data demand increases, we can see that the traditional configuration is not able to support this. So in response, to build a high-speed bus that can cater this, we require only a bridge between the processor's bus and the high-speed bus. So this is a new configuration known as the mezzanine architecture. Okay, I know this is a lot. Let's take some time to understand what this is. So we have the traditional bus architecture. The traditional bus architecture has an insulator. The first insulator is the cache. It insulates the processor from the traffic over here. And then we have another insulator or a buffer called the expansion bus interface. It insulates the traffic of the processor to the main memory from the I/O devices. So we have the system bus and the expansion bus. The expansion bus caters the I/O devices. The system bus caters the main memory and the cache to the processor. Okay. So, but the traditional configuration has its drawbacks. When the I/O devices demand more data, the bus obviously can't support this. So we introduce a different architecture. Okay, so the next one is called the high performance architecture or the mezzanine architecture. Oh, I forgot to crop this. Let me do that really quickly. Okay. So any questions so far? Is everyone okay? So far, so good?
So far, so good.
Okay, so I have a chat here. Let me see. Okay, all right, great. Okay, so the next one is the mezzanine architecture or the high performance architecture, supposedly used to overcome the drawbacks of the traditional configuration. So in general, if a great number of devices are connected to the bus, the performance will suffer, obviously. There are two main causes. The first one, in general, the more devices attached to the bus, the greater the bus length, and hence the greater the propagation delay. When the control of the bus passes from one device to another frequently, of course, there is going to be some decision-making or coordination going on, and that contributes to the delay. And second, the bus may become a bottleneck as the data transfer demand approaches the capacity of the bus. This problem can be countered to some extent by increasing the data rate of the bus, by using wider buses, which we have seen. However, because the data rates generated by attached devices are growing rapidly, ultimately, how far can it go, right? So let's talk about the next architecture. So the next architecture, which is the high performance, we have the processor, we still have the local bus with the processor and the cache, but the cache is directly connected to the system bus and the system bus is connected to the main memory. So here we have the cache bridge connected to the high-speed bus, and we have the expansion bus interface connected to the expansion bus. Now we have two buses in comparison with the previous one, which we only had the expansion bus. Here we have the high-speed bus. The system bus, we had it before. The expansion bus, we had it before. This is the only one that's different, the high-speed bus. So the high-speed bus, what does it do? The cache controller is integrated into a bridge or buffering device. So you can see that it is directly connected to the high-speed bus. That connects to high-speed bus. This bus supports connection to high-speed, high-capacity I/O devices, such as graphics workstation controller, as well as interface controllers to local peripheral. What does that mean? Means that the high-speed bus handles I/O devices that require really high demand. And at the same time, it also handles this controller over here. This controller over here, or this buffer, handles the slowpoke devices, such as the fax machine, which we don't have anymore, the modem and serial ports, handling printers and stuff like that. So in this structure, we have the high-speed bus catered specifically to high demand I/O devices, and the low ones, the low I/O devices, the low demand I/O devices is handled by the expansion bus. So you have that separation. So the advantage of this architecture is that the high-speed bus brings high demand devices closer to integration with the processor. So it's close, it is a step closer to the processor, and the low ones is further away. Changes in the processor architecture do not affect the high-speed bus and vice versa, because you have this insulator or the buffer known as the cache, and we have the insulator for the slowpokes and the fast ones, which is the expansion bus interface. So our insulators are very, very important. They help to have some independency. So any questions about this one? Okay, so I think I wrote quite a lot in your slides, so you can read back if you can't keep up. But if you want me to repeat, please let me know. Okay. And we also talked about the elements of bus design yesterday, and we talked about the two different types of bus design, which is the dedicated and the multiplex. And I briefly told you what dedicated and multiplex is. So here today, we're going to dive a bit more into what is dedicated and multiplexed. So a dedicated bus line is permanently assigned either to one function or a physical subset. So you have one function or a physical subset. So what is a functional dedication? So one bus has only one function. That's the name, functional dedication. Is used to separate dedicated address and data lines. So the bus line is used to handle the address, and another bus line is handling the data. This is common to many buses, but it is not essential. And then we have the physical dedication, which refers to the use of multiple buses, each of which connects only a subset of modules. So we have multiple buses connecting to different modules, multiple modules. A typical example of this is the use of an I/O bus to interconnect all the I/O modules. So we have the I/O bus. Let's assume this is our I/O bus, and it is connected to multiple I/O modules. We know that the I/O modules is not only one, right? We have many, many modules, as well as the memory modules. So this whole I/O bus is connected to all of the I/O modules. This bus is then connected to the main bus through some type of I/O adapter module. So you have like an adapter over here. This is a very poor drawing, really sorry. Adapter over here that connects to the main bus. Assuming this is the main bus. This is a very poor drawing. I hope I'm not confusing you guys. Okay, so we have the I/O bus connecting to all the I/O modules. We have some sort of adapter, of course, to connect the I/O bus to the main bus. So the I/O bus here is the physical dedication the type, the physical dedication bus type. So the potential advantage of physical dedication is high throughput because there is less bus contention. What does contention mean? It means disagreement or the need for coordination. So throughput is more data over a smaller amount, over a small period of time, because there is less disagreement among the devices. A disadvantage of this, however, is the increased size and cost of the system. So you can imagine it like you have a manager handling the whole department. And then for another department, you have another manager. And for another department, you have another manager. You don't necessarily need a manager. Sometimes the people inside the department can become the manager itself. But because you want a physical dedication, you specifically hire a manager from somewhere else. So basically you are increasing the size and also the cost of the system. You are increasing the size of the department because you're adding extra person, which is the manager, and you have to pay more because you have to hire the manager. So it's not necessary, but sometimes they use a system like that. Okay. So that is physical dedication, and another is functional dedication, which is a bus for a specific function. Okay, moving on to the next one, next type, which is multiplex. So a method of using the same lines for multiple purposes. This is what multiplex means. You can use fewer lines, use less space, and is usually cost efficient. However, the downside is it has to be able to handle these multiple functions or these multiple devices, which makes it, how do you say it, more intelligent. So because of that, it needs a more complex circuitry. Okay, so for example, address and data information may be transmitted over the same set of lines using an address valid control line. So this is our bus. At the beginning of the data transfer, the address is placed on this bus and the address valid line is activated. Okay, so this is our bus. I'm not going to draw because my drawing is pretty bad. This is our bus. So at this point, each module has a specified period of time to copy the address. Okay, we have not talked about time yet. So each module has a specified period of time to copy the address. Maybe time slot number 1 is for a module, IO module. Time slot number 2 is for the memory module, for example. So at this point, each module has a specified period of time to copy the address and determine if it is the addressed module. Meaning to say, I call out to an address. This address possibly belongs to the memory module, but the memory module and the IO module does not know this. So what they have to do is they have to see if this address belongs to them or not. So, and if they see the address and say, and the memory module recognizes this address, hey, this address belongs to me, so I need to respond. So for that to happen, they have to read it at different time slots. So each module has specified period of time to copy the address and decide whether they have to respond to it or not. The address is then removed from the bus, from this bus, and the same bus connection are used for the subsequent read or write data transfer. After the module has recognized, hey, this address belongs to me, I should respond to it, and then the CPU withdraws this address and puts in the data for reading or writing. Okay, so the bus has to handle multiple things according to time. I hope that makes sense. Is that okay with everyone? We'll see the timing in a bit after this, the timing synchronous and asynchronous. So hopefully that makes much more sense after that. And then we have the method of arbitration. Am I done here? Okay, yes. So the next element of bus design is method of arbitration. And I told you arbitration is basically having someone to decide. That is what it means, having someone as the decision maker. So there are two types of this method, which is centralized and also distributed. So for centralized, you have a controller to decide. For distributed, you have a meeting among yourselves and you come to an agreement among yourselves. So that is distributed. So In a centralized scheme, a single hardware device referred to as a bus controller, you have their controller, like a manager as well, or arbiter, is responsible for allocating time on the bus. So time slot number 1, I/O module, you go first. Time slot number 2, memory module, you go next, something like that. The device may be a separate module or be part of the processor. Whereas in a distributed scheme, there is no central controller. Each module contains access control logic, and the modules act together to share a bus. Again, they have a meeting, they decide. So the purpose is to designate only one device, either the processor or an I/O module, as the master. So the arbitration will assign a master, and once it has decided who the master is, the rest is going to be slaves. The master may then initiate a data transfer with some other device which acts as slave. Okay, so one person or one module becomes the master. And this is done through the method of arbitration. Okay. So far, so good? We'll take a break in 15 minutes, okay? So let's continue with timing of synchronous bus operations. We have two types, which is synchronous and also asynchronous. I told you synchronous, it happens at the same time. Asynchronous, it doesn't happen at the same time, obviously. Okay, so here we have, over here we have a clock cycle. A clock cycle is a sequence of binary digits of ones and zeros. So you have over here 1, you have a 0 over here, 1, 0, 1, 0. It is a sequence of ones and zeros. This is your clock. This is what your clock does. And 1 and 0 makes one clock cycle. We can also call this as one time slot. This is also called a bus cycle, but typically they call it as a time slot. Okay, so in this example, we have 3 time slots, just for basic explanation. It's not 3 time slots all the time. So here we have the status lines. The status line is controlled by the CPU. So let me write that over here, the CPU or the processor. Then we have the address line, the address enable. We have the read cycle operation, and we have the write cycle operation. Let's talk about it one by one. Okay, but first, the clock over here can be read by all devices, by all modules. They have access to this clock. So the clock is like a universal clock for everyone. You can't have a clock only specific to the I/O module. It doesn't work that way. Once you have a clock, everyone can read this clock. Hey, let's start at the same time. So this is what the function of the clock is. So most events occupy a single clock cycle. Not always, but typically. And bus signals may change at the leading edge of the clock signal. So what is a leading edge? This is a leading edge. This is a leading edge. So you will see inputs coming in at leading edge. Maybe it's slightly delayed, but most of the time they will start at the beginning of a clock cycle. So this happens at the leading edge. Okay, moving on to the next one. So I already wrote my notes over here for you guys to refer to later. So the processor places a memory address. So over here, we see that the processor, this is our processor, it gives out signals over time. You can see that over the 3 clock cycles, the status signal is there. It's not going anywhere because it is constantly controlling something. So the processor decides, okay, I want to put an address in the address line. So this is your input of stable address. Sorry, it puts in the address. And after some time, it becomes stable. How do you know if it's stable? This is when it starts to become stable, when it starts to have like a straight line. So when it is stable, the CPU enables the address. Once the address lines have stabilized, the processor issues an address enable signal. So the CPU addresses the enable line. Sorry, enables the address enable. Sorry, what was that? Issues an address enable signal. Oh my God. So it addresses, okay, I need to say that properly. It issues an address enable signal. Okay, so this is your signal. This is your signal. Okay, what just happened? This is our CPU. It is constantly giving out status or control signals, and it decides to put in an address in the address line. Once the address is stable inside this line or this bus line, the CPU says, okay, now we can enable the address, and we issue the address enable signal. So this is our signal. Okay. A memory module recognizes the address, and after a delay of 1 cycle, places the data on the data lines. Sorry, I skipped this. For a read operation, the processor issues a read command. So we have two operations, right? This is the operation of read, and this is operation of write. Let's go for the read one first. For a read operation, the processor issues a read command. So here you see that it issues a read command signal. This is a signal. This is a signal. This is data. This is data. I forgot to tell you. This is data. So the ups and downs is signal, and something looking like this is the data. So sometimes you put in the data first, and then you call out the signal. Sometimes you put in the signal and you call out the signal and put in the data next. So for the read, you put in the signal read first. You call out, you issue a read signal at the second time slot over here. Okay, let me erase all of this first. In the read cycle, you call out the read signal, and this happens at time slot 2, and issues a read command at the start of the second cycle. A memory module recognizes the address, and after a delay of 1 cycle, places the data on the data lines. So after 1 cycle, the memory module recognizes this and places the data on the data line. Okay, so this is for the read. So then the processor responds and reads the data from the data line and drops the read signal. So here you can see that the read signal is dropped because it is done reading the data from the memory, and then the memory ends. Okay, so that is for read cycle. I'm gonna go over this again, don't worry. And then we have the write cycle. First, you can see that the data is put into the data line first. This is the opposite case for the read. For the read, we issue the read signal first. For the write, we put in the data first into the data line. The processor puts the data on the data line at the start of the second cycle and issues a write command after the data lines have stabilized. So once it has stabilized over here, the processor issues a write signal, and the memory module copies the information from the data line. So it copies during the third clock cycle over here, and then the processor drops the write signal. Okay, so again, I'm going to repeat that. We have 3 time slots over here. Our clock can be read by all devices, by all modules. Everything must start at the beginning of a clock cycle. No one gets to begin before the clock starts. Okay, and then we have two types of data here, not data. One is the signal and one is the data. Data can be in the form of address, or data can be in the form of data to be read or write. Okay, and then I also told you that when this data has a straight line, it indicates that it is stable. And for a read cycle operation, you call out the read signal first. For a write cycle operation, you put in the data first and then you only write. Because if you call out write first, what will you write if there's no data, right? But if you were to call out read, yeah, that logic doesn't work. Okay, just remember the sequence. So the read cycle operation, you call out the read signal first, and then the data is put into the data line. Okay. What else? For this one, is there any questions about this one?
No, Doctor.
Doctor, I have a question.
Yes.
Are we saying that when the clock is triggered, only the event is happens, or we said when the clock is one, the event is happened for these cases?
When are you I would like to rephrase that question. You are saying that the event happens after the previous event, or does it happen according to the clock cycle? Is that your question?
And let me repeat my questions.
Okay.
So let's say the clock. So the event happens when the clock is triggered from low to high, and then the event occurs, or it is when the clock is one, the event is happened. For this case, I'm not sure because I didn't saw the triggered things.
You didn't saw the triggered things. Meaning to say on the different time slots?
Kinda.
You're asking me, you are not seeing the trigger and suddenly it's being called out. Is that it?
Yeah, I'm just curious, like, let's see the second time slots. Let's say the read cycle is up, the read cycle is triggered,
Yes.
and it will wait until the third cycle, only they will take the data rights.
The memory module has to respond first, right? The memory module has to respond. It puts in the data. When the data is available, then the reading happens in the third time slot. And once the processor is done reading, it drops the signal and the data is also dropped. Does that make sense? Because it has this trigger, the memory has to respond to this first. It has to recognize this first. That's why it happens after a one-time cycle. Does that make sense?
Okay, then about the read cycle and the write cycle, we have the read line and the write line, right? And then will it be, how to say it, affected by the clocks? Means it will need to be like, if the clock is one only, it can be turns on, or it is depends.
Okay.
Can I just add on to this?
Yes.
Wait, Zidane, if I'm not mistaken, are you asking if it's level or edge triggered?
Yes. Does it.
If it's leveled or triggered.
Level or edge triggered, because like it's hard to say.
Oh, okay.
Whether the signals go at the level or they go when it's one.
Okay, understand. Okay. Okay, to answer that question, it depends on whether the operation is between two different modules or if it is within the same module. For example, for the write cycle, we see that this is from the processor. Let me write it as CPU because it's shorter. So this CPU already knows it's putting in data in the data line. It already knows. So it doesn't need to wait for one time cycle to respond to this. So what happens is that it calls out or it triggers the right signal. It doesn't have to wait until one cycle is done and then put out the trigger. It can immediately start or it has some delay to it. So I wouldn't say that the trigger is at the leading edge or at the level edge or at the level. So this is between the CPU. Okay, so it doesn't have to wait. Okay, whereas for the read cycle, this is triggered by the CPU. The CPU wants to read from the memory. The memory does not know this yet. So the memory has to recognize this, and in return, it has to process this within one time cycle, and then it puts in the data for the processor to read. So you see that there is a time gap over here. Whereas this one, it doesn't need to really wait, but there is a slight delay in the write signal. So to answer your question, whether it has to occur at the leading edge or at the level, not necessarily, but they have mentioned earlier that most things happen at the leading edge. Sometimes there is a slight delay, but I wouldn't focus on this so much. Does that make sense?
Okay, doctor. Thank you.
Okay. Hopefully that answers the question. It's quite confusing. Okay, so this is between the CPU. So it doesn't really have to wait, but you see that there is a slight delay because, of course, it's not very efficient. Whereas this is between the CPU and the memory. So the memory has to respond, but first to respond, it has to recognize that the CPU is calling out to me or the memory. So it happens later on. As for the signal, you can see that some are triggered. Wait, let's see. Some are triggered in between. Some are triggered at the starting of the time slot. You can see that if it's in between the time slot, this is between the CPU and the CPU. You don't have to really wait. But if it is a new thing, or if it is between two different modules, then you have to wait between the time cycles. Hope that makes sense. I have a chat over here. Level or edge? Oh, okay. Thank you, Tabina, for the question, for adding on to that. Okay.
Doctor, just to clarify,
Mm-hmm.
so meaning that if it is within the same module, it doesn't matter whether the clock is at 1 or 0, it will happen within that cycle.
Yes, it can happen within the cycle. Correct.
Okay. Right. Thank you.
All right. Okay, so moving on, that was synchronous. Now we are talking about timing of asynchronous. So I think you will appreciate the asynchronous more because it's not as confusing. With asynchronous timing, the occurrence of one event on a bus follows and depends on the occurrence of a previous event. So one event happens, and then the next, and then the next. There's no like, it's not like the synchronous basically. So the processor places address and status signal on the bus. So it puts in the status signal and address on the bus. So this is where it controls everything, and it puts in the address in the address line. So once this address is stabilized, where is it? Once these signals stabilize, the processor issues a read command to indicate the presence of a valid address and control signal. So the processor we are still talking about the processor here. It issues a read command over here. Okay, so instead of going up, it's going down. Doesn't really matter. It's just a trigger. So it issues a read command, and then the appropriate memory decodes the address and responds by placing the data on the data line. So it wants to read, the CPU wants to read. Of course, it's going to read from the memory or the IO. In this case, it's the memory. So the memory responds to this and puts in the valid data onto the data line. And then once it has stabilized, it lets the processor know by putting in the acknowledge trigger. Once the data lines have stabilized, the memory module asserts the acknowledge line to signal to the processor that the data is available. So the memory, this is the memory. Oops. Where is my eraser? So this is done by the memory. The memory puts in the data. Once it has stabilized, it lets the processor know via the acknowledge line to tell the CPU, hey, my data is here, go ahead and read it. And then once the master, which in this case is the processor, has read the data from the data line, it deasserts the read signal. So now it drops the read signal. This causes the memory module to drop the data and acknowledge line. So once this is over, I mean the trigger is gone, the memory drops the data and also the acknowledge line. So this is the memory and this is our CPU. Okay. Finally, once acknowledge line is dropped, the master removes the address information. So the address information always goes last. Always goes last in the asynchronous timing. So basically, you have your memory dropping the valid data and dropping the acknowledge line, but in the CPU, the address is still there because the address is dropped last. I want to emphasize on that. The address is dropped last. Okay, do we have another example on this? Is this the same one? What's the difference between this one? Oh, so sorry. This one is for read cycle operation. Not very visible, but it's here. System bus read cycle. This is our read operation. And then what about write operation? Okay, so again, our CPU, this is our CPU. Let me just write it here over here. The CPU puts in the status signal, controls everything, and it puts in the stable address. And here, the memory module responds to the write command. Oh, sorry. At the same time, it puts signal on the status. Oh, I skipped the step. It puts the CPU, sorry, the CPU puts in the stable address and the status signal. And then once it stabilizes, it triggers the write signal. This is also the CPU, triggers the write signal. The memory module responds to the write command by copying the data from the data lines and asserting the acknowledge line. So all the way. So the CPU wants to write to the memory module. Sorry, I forgot what this was. Okay, let me repeat that. Okay, so first the CPU puts in the status signal and the stable address and also the valid data because it already knows what it wants to do, right? So it puts in the data and then once it has stabilized, it becomes flat, it triggers the write signal. And then the memory module responds to this. Again, you see that it takes some time, but there's no time slot over here. It takes some time to recognize this, and it responds by copying the data from the data lines and asserting the acknowledge line. Say, this acknowledge line basically tells the CPU, hey, I recognize your signal. I'm doing what you're asking me to do. And then once this acknowledge line is, once the CPU has been alerted on this, it drops the write signal. And then the master drops the write signal and the memory module drops the acknowledge sign. And then the CPU drops the address. But I didn't put it here. So this is the last thing that gets dropped as usual. Okay, so that is the difference between the write and the read. The read, what's the difference? For the read, you trigger the read first and then the valid data from the memory is put on the line. Whereas for the write, the CPU knows what it's going to do. It puts in the data on the line together at the start. Okay. So there's no time slots involved. Only is this event done yet? Okay, next event. Is this event done yet? Okay, next event. There's no time slots involved. They are all waiting based on the acknowledge line. So the acknowledge line is the way that they coordinate themselves. Is that okay? Any questions?
Doctor, I have a question.
Yes.
If you go back to the read cycle, I mean like the what we call the drop of the data lines is later than the read. I mean read what we call it stop earlier than the data lines. Is that means that all the data, I mean the last data will be lost because of this? Is there any data lost?
Is there any data loss?
Yeah.
Because the read is done by the CPU, right? If the CPU decides that it has read enough of what it needs to be read, then it drops off the read signal. Because the data is given by the memory. The memory doesn't know when the CPU is done. So the only way for the memory to know that the data is no longer needed in the line is when the CPU drops this trigger. This is why the CPU has to drop the read signal, and then the memory says, oh, the CPU is done. Okay, let's take back the data. Because the data is just there. It's available in the line.
Okay. Okay.
Okay, so this is, I need to clarify this. When you put in the data, it's not to say that the data keeps on increasing. This indicates the time. This indicates the time that it is present in the line. Okay, so if I drop it here, it doesn't mean that, oh, this portion of the data is not read. That is not what it means. This length or this how long it is indicates how long it is inside the line, not how much data it is providing. Does that make sense?
Yes, sir.
Okay, so you can imagine it like a ball. I hope this analogy is going to make sense. I'm putting a ball inside a pipe, right? And I want to wiggle this ball inside the pipe. And my aim is to see that the ball wiggling inside the pipe. So I'm just going to wiggle it, and that is my aim. And the ball is just the ball. And the time, how do I say this? This is a bad analogy. I need to rethink this analogy. Give me a minute. How do I say this? Does anyone have a good analogy? I need to think about this. Okay, nothing is coming to my mind. Let's take a break. 10 minutes is okay for everyone? Let's come back at 3:06. Hopefully I can come up with some sort of analogy that makes sense. Okay, let's come back at 3:06 p.m. Take your break, take some drink, go to the toilet. I'll see you in 10 minutes. If you have any questions, you can ask me now as well.
Doctor, can you just explain back about the centralized scheme and the distributed scheme?
The centralized and the distributed. Okay.
It's an elements of the bus design. This part, yeah.
Okay, so the method of arbitration. Okay. Am I still recording? Okay, yes, I am. Okay, so the method of arbitration, we have two types, which is the centralized and the distributed. And I told you in the centralized scheme, you have a bus controller. You know that you have many bus systems, right? You have a bus system, you have the local bus, etc., etc. And then you have a bus controller. The bus controller, what it does is that it is responsible to allocate time on the bus. Okay, let's see. How can I draw this in a way that won't confuse anyone? So the bus is connected to many devices. Okay, and then we have a controller over here. Controller bus. So it is responsible to allocate time on the bus, meaning to say what gets called first, who puts in data into the bus, that we have seen happening here, right? So there is a bus controller deciding who gets to use time slot number 1, who gets to use time slot number 2, etc. So you have a manager doing that, allocating the time for the time slots to be used by the modules. Whereas for the distributed scheme, there is no controller. The time slot is not decided but to be used by any modules, but the modules see that who is calling, who is signaling to call out, to issue a signal. And from there, they decide who gets to go first. So there is no one deciding, but they have like some sort of an agreement. So each module contains access control logic. So this is necessary for them to do this decision, and the modules act together to share a bus. So I would say this is not between devices. We don't have an example of this happening. So I'm going to tell you this in layman terms. Hopefully it's better. You have your manager. The manager is the admin of our department. And for 2 to 3 p.m., the manager or the admin decides that this is my class ECC 3204. And from 3 to 4, they decided, okay, a different class ENG 3004 stats. And then at different time, a different module gets to go. 4 to 5, let's say IDP class. So this is what the bus controller does. It decides who gets to go or who gets to use a time slot. It acts like a manager. Whereas for the distributed scheme, you don't have this manager, but everyone is capable, or the modules inside this bus connected to this bus is capable of making this decision in a way that if they were to trigger at the same time, they would see which came first or which is more priority or which is more efficient to go first. So they have that kind of intelligence to them. So the distributed scheme will have to be more, they will have to be some sort of, will have to have some sort of intelligence, making it a little bit complex as compared to the bus controller. Okay, so it's just, is that okay?
Yeah, it's okay.
All right.
Thank you, Doctor.
All right. Okay, 5 minutes to go. Excuse me. Okay, whoops, I went over time. So is everyone back? Let's try to have an analogy on this one. Hopefully I don't mess up. Okay, so let me try to explain this again. So one of your classmates is confused. What happens to the data if the write signal is dropped? Because the data is still there. What happens to the data is some packet lost or is some data lost. So this is not how you visualize the data inside a bus. So whenever you see this line, it simply is a time frame. So to put this into perspective, hopefully I have a hollow pipe, which means that you can't see through it. And then I want someone to see, this very cute person, to see that whatever that is going on in this pipe, I want them to draw it. Okay, I want them to draw it. In this case, we are asking them to write, draw, write. Okay, let's put write over here. Whatever you see in this hollow pipe, write it or draw it. So the data in this case would be, I'm already laughing because I know my drawing is going to suck. So my data is an 8-ball. Okay, so this is my data. I put it inside the hollow pipe. And when it comes to this cute person's eyesight, he sees the 8-ball inside this. He said, oh, there's data on the data line. Let me write, and then the instruction was to write it, right? That was given by the CPU. The CPU triggered this write signal. Whatever that is placed into this hollow pipe, you draw it or you write it. And this is received by the memory. The memory copies whatever that it sees inside this hollow pipe. It doesn't take the data, it only copies. And the 8-ball is now on the memory module. Okay, so what happens to the data? Once the CPU sees that this person has drawn or has written the data that it wants it to write on the memory module, it says, okay, the job is done. Let's call off the write signal. Let's call off the write signal, meaning to say the instruction is no longer there, but the data is still there, right? Okay, what happens to the data? Because the write signal is no longer there, suddenly there exists a portal over here that drops the ball. Okay, the portal only comes if the instruction to write disappears. So the 8-ball now disappears from the bus line. That was bizarre, but hopefully that makes sense. Okay, so if you don't want to use this analogy, please just take it as it is, because my brain doesn't work really well with analogy. If this makes sense to you, great. If not, you read it and you try to understand it. Any questions about this one?
No, Doctor.
Okay, so great. So we can move on. Okay. Okay, so the timing of bus operations, we talked about the synchronous and the asynchronous. We saw the synchronous has time slots, whereas the asynchronous depends on the sequence of the previous events. So the occurrence of events on the bus is determined by the clock line, whereas asynchronous, you don't have the clock line, but you have the acknowledge line to communicate with each other. In this case, the CPU was communicating with the artist, and the artist was drawing whatever that it saw inside the line. So the synchronous is simpler to implement and test, even though it looks hard to us. For the machine, it is simpler because it's straightforward. This time is used for this time. For this module, this time is used for this module. However, it is less flexible than asynchronous timing because all devices on a synchronous bus are tied to a fixed clock rate. The system cannot take advantage of advances in device performance. Let's say you have a device that responds really fast and doesn't need to wait one clock cycle. You can't take advantage of that because you still have to wait for one clock cycle. Whereas for the asynchronous, if the device can respond faster, great. just go faster. Okay, so a mixture of slow and fast devices using older and newer technology can share a bus for the asynchronous bus. So there are pros and cons to both. Okay, so that was bus. That was the first interconnection structure. The next interconnection structure is the point-to-point interconnect. The point-to-point interconnect. So why is there the need for point-to-point interconnect? So the principal reason for change from the bus to the point-to-point interconnect was the electrical constraints encountered by increasing the frequency of wide synchronous buses. So the bus could not handle the increasing frequency. At higher and higher data rates, it became increasingly difficult to perform synchronization because the bus either has to synchronize using a bus controller or they have the distributed scheme. And even so, with the bus controller, there exists some delay because the bus is constrained by its capabilities. So increasingly difficult to perform the synchronization and arbitration functions in a timely fashion. So sometimes the bus is too slow to keep up. And then a conventional shared bus on the same chip magnify the difficulties of increasing bus data rate and also difficult to reduce the bus latency. So latency is how fast a data reaches another point. Latency is how fast a data reaches from one point to another. So that is latency. So it is difficult to reduce the latency. Or in other words, it takes a long time to transfer the data. So that it is difficult to increase the bus data rate and to keep up fast data transfer. So the point-to-point interconnect has lower latency than the bus, has higher data rate than the bus, and has better scalability. So the issues faced with the bus is overcome by the point-to-point interconnect, and we will see how it does that. Okay, so the first one of point-to-point interconnect is the QPI, or the Quick Path Interconnect. So the Quick Path Interconnect is introduced in 2008. Now you're asking me, why are we learning about stuff that happened before? Why are we not learning technologies up to date? Because if you only learn about the up-to-date systems, what if you design something and you go back to the past? So to avoid that, you need to know the previous ones and also the up-to-date ones, right? So this is why we have to learn the history of the processor, or like the machine. So it is introduced in 2008, multiple direct connections. So you would know which architecture has been done, why it didn't work, and what's the next best thing. So this is why we have to learn this. So direct pairwise connections to other components. It has a pair connection, eliminating the need for arbitration. So you don't need to do this decision making that we've seen in the bus. And then we have layered protocol architecture. These processor level interconnects use a layered protocol architecture rather than a simple use of control signal like the bus controller in shared bus arrangement. So instead of having one controller doing everything, they have layers to distribute the task basically. And then we use packetized data transfer. Data are sent in a sequence of packets, of which includes control headers and error control codes to compensate for any offset or delays. So in comparison to the bus, we saw that the bus was streaming in raw bits, right? But for point-to-point interconnect, we will see that they use packets. Okay. So this is a multi-core configuration using QPI. So you can see over here, let's talk about this diagram first. So you see that we have 4 cores over here, core A, B, C, and D. The cores have pairs connected. The line is called the QPI. You can see that the QPI exists in pairs. It's not bidirectional. One arrow only goes in one direction. It's not bidirectional like this guy over here. It only goes in one direction. Therefore, it exists in pairs to help to have the two-way system. So core A is connected to core B, core A is connected to core C, core B is connected to core A, core B is connected to core D, core C is connected to core D, core C is connected to core A. They usually communicate with their, how do I say this? 90 degrees partner. Don't know how to say this. It's not really 90 degrees, isn't it? It is 90 degrees. Okay, it communicates like this. So if the core A wants to communicate with core D, let's see, if core A needs to access the memory controller in core D, it sends its request through either cores B or C. It has to communicate this way to get this line over here, which must in turn, core B or core C must forward this request to core D over here. I don't know why it's like that, but it is. This is how the QPI works. And the core is connected to the I/O hubs, and the I/O hubs are called IOH, is connected to I/O devices. Over here, it is bidirectional. You can exchange data. And the core is connected bidirectionally to memory bus to the dynamic random access memory, DRAM. I think I wrote it in my notes somewhere. Okay, I did. Okay, so in larger systems with more than 8 processors can be built using processors with 3 links and routing traffic through intermediate processors. Okay, let's just ignore this part first. So the QPI is used to connect to an I/O module. So this is our switch fabric, QPI. The green arrows are the QPI fabric switch. And the QPI is used to connect to an I/O module via the I/O hub. The I/O hub or the IOH acts as a switch directing traffic to and from the I/O devices. The link from the IOH to the I/O device controller uses a technology called the PCI Express. So we will talk about the PCI Express later over here. Okay, so the PCI Express is from the I/O hub to the I/O device. A core also links to a main memory module. Typically, the memory uses dynamic access random memory technology using a dedicated memory bus. So the core is also linked to the main memory module. This is bidirectional, right? So you have that exchange data going on. And this is the dynamic random access memory. So here, this is the QPI multi-core configuration, but in the coming years, Intel decided to drop the QPI configuration and replace it with something else. And you can read further over here. Why did Intel drop the QPI bus from its CPU when its throughput was more than what they currently use? So this is further reading. It's not mandatory. If you are curious, you can read it. Okay, so let's talk about the layers. So the point-to-point interconnect, the good thing about it is that it handles traffic using layers. So the QPI layer, we have 4 layers. The first one is the physical, we have the link, we have the routing, and the protocol. For layers, we typically talk about the bottom part first, and then we go upwards. So the physical layer consists of actual wires carrying the signals, as well as circuitry and logic to support ancillary features required in the transmission and receipt of ones and zeros. So here you are transmitting bits. The unit of transfer at the physical layer is 20 bits. So between these 2 layers, you are transmitting 20 bits at a time, depending on how much transfer is going on per second. So 20 bits is called FIT. It's called FIT, which means physical unit. The unit of transfer is physical units or FITs. And then we see the second layer, which is link. It is responsible for reliable transmission and flow control. So the link ensures that everything is reliable and the flow is good. So here, the transfer or the unit of transfer is 80-bit. The fit is 20. The flit is 80. Flit refers to flow control unit and is 80 bits in length. Okay, so 80 and 20. And then we have the routing. The routing tells us the possible path that the packets can go through. If you have more devices connected, then you would have like a million puzzles to solve, or like a million pathways, not a million, let's say 100 paths that you can choose from. So the routing takes care of this. It provides the framework for directing packets through the fabric. The fabric is the QPI. The QPI, which is the green arrows. So the high-level set of rules for, this is the protocol, the high-level set of rules for exchanging packets of data between devices. A packet is comprised of an integral number of flits. So one packet is a lot of numbers of flits. This is 20, this is 80, this is a lot more of flits. Okay, so moving on. I think this is just definition. So this is the physical layer. This is our physical layer. Remember the definition of the physical layer. It consists of actual wires carrying the signals, and the unit of transfer at its physical layer is 20 bits. So let's see if that really is the case. So this is our physical layer, which consists of actual wires. This is the wires. So here we see that the QPI port for the physical interface consists of 84 individual links grouped as follows. So you see over here that you have like roads. You have roads over here. Let me make this bigger. You have like roads over here. One road is called one lane, and one lane consists of two wires. One lane consists of two wires. So each data path consists of a pair of wires, two wires, referred to as a lane that transmits data 1 bit at a time. So only one data bit at a time. Thus, the QPI is capable of transmitting 20 bits in parallel. So let's see if this is actually 20. This is 5. This is 5. This is 5. And this is 5. So you have your 20 over here. So 20 bits in parallel at a time. Thus, the QPI is capable of transmitting 20 bits in parallel in each direction. What does it mean by each direction? This is the transmission and this is the reception. So they are moving in the opposite way. The data is moving. One is going down, the other is going up, because the transmission lane is over here and the transmission lane is over here for the other side. So you are capable of, the QPI is capable of transmitting 20 bits in each direction. This one is also 20 bits. This is 20 bits. It is grouped in 5, grouped in 5. Also 5 over here. Okay. Now, where did the 84 come from? Sorry, where did the 84 individual links come from? So if 20 bits mean that we have, so one bit has two lanes, or sorry, two wires, right? One bit has two wires over here. So if we have 20 bits or 20 lanes times 2, you only have 80 wires. So the other 4, corresponding to this guy, belongs to the clock. So you have 2 over here and 2 over here. So you have 40 and 40. So you have 84 in total individual links. Where does it say about the clock? Okay, so plus a clock lane in each direction. So for the transmission lane to the reception, you have the forward clock. For the reception lane, so for the transmission lane and the reception lane, you have the forward clock over here. So the forward clock belongs to the transmission. The receiving clock belongs to the reception. Okay. Let me erase this. Very messy. Okay, so here they are telling us Typical signaling speed of the link in current product, not current, past products, calls for operation of 6.4 gigatransfers per second. Gigatransfers per second. At 20 bits per transfer, that adds up to 16 gigabytes. So 1 byte is 8 bits, right? 1 byte is 8 bits. So now it's telling us this product in the past, I don't know what's the current transfer, is 6.4 gigatransfer per second. Gigatransfer. So if, let's do some math over here. So 6.4 gigatransfer per second times with 20 bits per second. We are focusing on one side of the QPI interface of the physical layer. 20 bits per transfer. Okay, 20 data links, transmit and receive. So the transfer cancels out with the transfer and you get 6.4 times with 20 gigabits per second. 6.4 times 20, or not 28. 20 is, I don't know. Let's use my calculator. 6.4 times 20, 128. So we would get 128 gigabits per second. So if we divide this by 8, we would get 16 gigabytes per second. And I'm only doing this part because I multiplied by 20 bits. So if I were to find out the total transmission, which is 40 bits, so basically you times this by 2 because 20 times 2. So you would get 32 gigabytes per second in total. So this is the total capacity if I were to provide the number of transfers per second. Is everyone okay with this math? Does anyone want me to repeat? This is a 2, not an L. Okay. So really sorry for the bad handwriting. I've been penalized in the past for my bad handwriting. Not proud of it. I'm trying my best to write nicely. Okay, so any questions about this one? Is everyone okay? It's 3:30. Let's continue for another 15 minutes, hopefully. Okay. Okay, so we talked about the QPI physical layer previously, and we saw that it has actual wires. And if they provide us the transfer per second, we can actually count the total capacity of the physical layer. And then we talk about the QPI multi-lane distribution. So another function performed by the physical layer, apart from transmitting the bits back and forth, is that it manages the translation between 80-bit flits, 80-bit flits and 20-bit flits, using a technique known as multi-lane distribution. So this is a bit stream of flits. Again, what is flits? Let's go back. Flit is 80-bit and fit is 20-bit. So this is a bit stream of flits, which is one of this is 80 bits. And then the multi-lane distribution, what it does is that it distributes these flits into lanes. And this scheme of distribution is known as the simple round robin scheme. What that means is that the number 1 goes here, and then the number 2 goes here, and then the number 3 goes here, number 4, number 5, up to n, and then n plus 1 goes over here, n plus 2, n plus 3, n plus 4, etc., etc. So it has that sequence going on where it goes from up to down and then goes back up again. Up to down, goes back up again, up to down. So this is called the simple round robin scheme. I don't have an analogy for this. Take it as it is. Okay, so this is the simple round robin scheme. It distributes the flits into lanes. This approach enables QPI to achieve very high data rates by implementing the physical link between two ports as multiple parallel channels. So when it distributes it like this, it allows to transmit the flits parallel instead of just one stream. Okay, so this is what the physical layer does. Apart from transmitting and receiving, it also manages the translation. Okay. All right. So the QPI link layer, we were talking about the physical layer. Now we are talking about the link layer going up one level. So it performs two key functions, which is the flow control and the error control. So it operates on the level of flits. We saw that the physical layer operate on flits. Flits is flow control unit. So you already have a hint here. Flit is flow unit. What does it do? Flow control. So each flit consists of 72-bit message payload and an 8-bit error control code called CRC. Maybe you've seen this term before. I'm not sure in which subject, but CRC is pretty famous. So you have your 72-bit payload and your 8-bit CRC over here. And then the two functions is flow control function and the error control function. So the flow control function needed to ensure that the sending QPI entity does not overwhelm a receiving QPI entity. Remember that you have the receiving and the transmission. So it manages this so that the QPI is not overwhelmed. So this is the function of the link layer. And then for the error control function, it detects and recovers from bit errors and isolate higher layers from experiencing bit errors. So if there were an offset, that offset would appear in the error code and it would not affect, but the payload is still there. The payload is not affected. So the higher levels, such as the protocol, will not be affected by this error in the lower level. So just remember that the QPI link layer functions to do these things. And then we have the QPI routing and protocol, the upper two layers. This is our this is our second, and this is our first layer. The topmost layer, the protocol. So the routing layer is used to determine the course that a packet will traverse. Basically, it determines how many paths can the data go through. It's like a maze. Find out the possible path to go out of this maze. So this is what the routing does. And then it decides which is the best path to use. And this is what it does. And this is defined by firmware and describe the possible paths that a packet can follow. And then for the protocol layer, the unit of transfer is called packet. The physical layer unit transfer is called FIT. The link layer is called FLIT, flow control unit, flow unit, and then the protocol layer, the unit transfer is packet. It's a unit. It's not really a packet, it's a unit. So a packet is defined as the unit of transfer. Was redundant. One key function performed at this level is cache coherency protocol. So this is its main function. I want you to remember the functions of each layer. We had for the flow control unit, and now we're talking about the protocol layer and the routing, right? So the protocol layer function is to perform the cache coherency protocol. What that means is that it ensures that the cache is consistent. Multiple caches are consistent in data. And then a typical data packet payload is a block of data being sent to or from a cache. That's why the protocol layer needs to ensure that the values in the cache is consistent, because it is transferring the block of data to and from the cache. Okay, so the protocol layer deals with the cache. The routing layer deals with finding out the possible path for the packet. Okay. So how is everyone doing? Can we go for another 7 minutes or 10 minutes? Is everyone dying already? I have my coffee, so I'm not dying. Is everyone okay? Can I continue? Any questions?
No, that is also good. Okay,
Okay.
continue.
Let me see if there is any chat. Okay, no chat. So peripheral component interconnect. What is PCI? PCI, we have seen this, but only briefly. Let's go back. So the PCI, I talked to you about PCI Express, not necessarily PCI. So the PCI Express connects the I/O hub to the I/O device. Let's talk about the PCI first and the difference between PCI versus PCI Express. Okay, so we have the PCI. So PCI is a popular high bandwidth processor independent bus. So it is a bus that can function as a mezzanine or a peripheral bus. So we saw that the PCI Express was connected to the IOH or the IO hub, and the IO hub is connected by the PCI to the IO devices. So in a way, it functions like a bus. So it is for high bandwidth bus. It is a high bandwidth bus. So it delivers better system performance for high speed IO subsystems. So what's the difference to a common bus? It is high bandwidth. So there are PCI special interest group, and we also have PCI Express. We will only talk about the PCI Express moving on. So the point-to-point interconnect scheme intended to replace bus-based schemes such as PCI. So the PCI, as I told you before, it has high bandwidth. It is better than the regular bus, even though it functions in a way like a bus as well, because it connects the I/O hub to the I/O devices. The key requirement is high capacity to support the needs of higher data rate I/O devices, such as the gigabit Ethernet. Another requirement deals with the need to support time-dependent data streams, and we will see how that is. Okay. So this is a typical configuration using the PCI Express. So let's ignore PCI now. Let's focus on PCI Express first. So here we have a chipset. The chipset is connected to the PCI Express. The chipset also is connected to the core and also to the memory. So we can say that the chipset acts like a buffering device between the core and the memory to the PCI Express. The PCI Express indicated in green is like a switching, what's the right word to use this? It's like a switching line. It's like a switching line, even though I have a switch over here, but this is the device. So it is like a switching fabric. It's like, how do I say this? It's like a maze where you can put in a lot of devices. Let's just stick to that first. Okay, so the PCI Express, so the chipset acts as a buffering device to deal with difference in data rates between the I/O controllers and the memory and processor components. So these guys, they speak a different language. These guys, they speak a different language. So the chipset acts like a buffering device to deal with the difference in data rates. So to help the synchronization. And then the chipset also translates between the PCI Express transaction formats and the processor memory signal and control requirement. Like I said to you before, the core and the memory, maybe they talk in different languages, and these devices connected to the PCI Express talk in different formats, talk in different lengths. So the chipset helps to synchronize that or translate that. And then the chipset typically supports multiple PCI Express ports. So you can see that you have multiple ports over here, some directly to the device itself if the device requires high demand data or high demand capacity, and some can be connected to a switch for devices that don't require really high capacity. So here you can see that there is a PCI Express endpoint, and here we have a legacy endpoint. So a legacy endpoint is, how do I say this? It's like an old system that the PCI Express is tolerating. How do I say this? The architecture is slightly different, but they are able to communicate even though the architecture is different. It's like you are tolerating an old friend even though the old friend annoys you. So this is like the legacy endpoint. He's old, but he's valuable, so I'm going to tolerate him. So this is the legacy endpoint, and these PCI endpoints are just regular I/O devices. What time is it? Okay, let's go for a bit. One more slide. I wanted to finish a lecture chapter 3, but I don't think I can. Okay, so we have the protocol layers now. As with QPI, the PCI Express also has layers. The QPI has 4. The PCI Express has 3 layers. We have the physical. Instead of the link, we have the data link, slightly different. And then instead of a routing and protocol, we have the transaction. But these are called protocol layers. Whereas for the QPI, we call them layers, just layers, not protocol layers. So you can refer back to the slide. They are slightly different. Please take note on the difference. Okay, so the reason why I put this pin is because I don't want you to think this is a bidirectional data exchange or something like that. So it needs to be an icon that is slightly cartoonish. So it's ugly, but it works, right? So first, the physical consists of the actual wires carrying the signals, almost similar to the QPI. You have actual wires. You have the port up and down, the lines, and the lines, 2 lines respond to a lane, 1 lane transfers a bit. That was in the QPI. But for this one, we will see what it does. It also carries ones and zeros like the QPI. And then we have the data link. It is responsible for reliable transmission and flow control. This is almost the same as the link layer in QPI, the same function. The data packets generated and consumed by the DLL are called the data link layer packets. Data link layer packets. So between the data link protocol layer, the exchange is in the form of data link layer packets. We don't call them flits. We don't call them fits. We call it as DLLP. And then we have the transaction. The transaction generates and consumes data packets. So this is where the data packets come from. It generates and consumes, and it manages the flow control of those packets. So this guy is responsible for reliable flow control. This guy manages. So it's almost redundant, right? But we need to talk more on this to see the difference. Okay. But in definition wise, it almost seems like similar, right? The data packets generated and consumed by the transaction layer are called the transaction layer packets. So the unit of transfer is transaction layer packets, whereas for the data link is data link layer packets, DLLP, and we have TLP. And the PCI Express also uses the round robin scheme. I believe that's the name, whereby this is a byte stream. Previously in the QPI, this was a flit stream. QPI, you had the flit stream, and then they distributed into lanes. Whereas for the PCI Express, you have the byte stream and you distribute it into lanes as well. Okay, so I'm going to end our class here, and we will continue back at the PCI Express multi-lane distribution in the next class. So have a great rest of the day. If you have any questions, you can ask now. Otherwise, class has ended. Thank you, everyone.
Dr. Can I see the previous slide before? There's a notes I missed.
Oh, okay, sure.
It's about multi-core configuration using QPI. I think the first one is it 2, I think. If I didn't know
The
that.
multi-core The QPI, is it
Yeah.
this one?
This is the second, the first one.
The first one. This one?
Yeah, there you go. Thank you.
Okay. What was the question? Or you just want to see it?
Yeah,
Okay.
thank you, Doctor.
You know, this slide is also available in Putra Blast in PDF. Okay. So any other questions? So one of your classmates asked me whether the exam is going to be done in MCQ, multiple choice questions, or is it going to be subjective? I haven't decided on that. I think there will be a mixture of both. Okay, but I will update you because I have not completely prepared the exam question yet. Any other questions? So we are
No,
good.
Doctor. That's it.
Okay, so I'll see everyone next week. Revise. It's a lot of input. Okay, so I'll see you next week. Bye-bye, guys. Take care.
You, Doctor.
Thank you, Doctor.
Everyone sound proceed.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you, Doctor.
Bye, guys.
Doctor, one more thing I want to ask. For the tutorial you give us before the exam, right? Tutorial.
The tutorial meaning assignment?
Something like that, exercise.
Yes,
or
I
something.
will.
Yeah. Okay, thank you.
Okay.